Welcome back. So, in the last lecture we obtained the expression for the propagator for the Kleene-Gordon equation. Let us quickly recap through that and then we will proceed to analyze the properties of the propagator. So, we started with the Kleene-Gordon field, the field equation, the Lagrangian for the field, which is given in the blue box here on your slide, and then we followed the prescription that was arrived at in the context of the harmonic oscillator. The correspondence between the harmonic oscillator operators and the field operators is given in the green box. Q t now because the harmonic oscillator in the quantum version is essentially 0 plus 1 dimensional field theory. So, q t now becomes phi x of t, depends on the space time variable, underlying space time variables, and the other expressions also follow similarly, and that is given in the green box right at the bottom of your slide, right hand corner. Then we introduce the I epsilon prescription by substituting m square minus I epsilon for m square to make the integrals converge, and this essentially operates as a damping factor. And we wrote down the expression for the generating functional as the expression for in the red box here, where we introduced a source term j of phi. J phi rather. The free field Lagrangian is the blue box, and the integration element, the path integration element now takes the path integration over all the field configurations. To obtain Z0j, we moved over from the position space to the Fourier space, the wave vector space, by making the Fourier transforms of the various field functions, and the expressions for which are given in the green box here. And on doing that, we arrive at the expression for the action in the Fourier space as the expression given in the green box right at the bottom of your slide, where the transformations are given by the Fourier representations. Phi x is equal to integral over dk 2 pi to the power 4 e to the power minus x minus I k x phi tilde of k, and similarly for the j x. We introduce the change of variables, chi tilde k now replacing phi tilde k with an additional term j tilde k upon k square minus m square. The entire thing is given in the red box right at the top right hand corner of your slide. And in terms of this new variable chi k, the expression for the action now takes the form given in the green box at the bottom of your slide. The interesting part here is, if you look carefully at the integrand of the action, the first term is independent of chi and the second term is independent of j. So, in a sense it operates to separate out the terms of involving the source of the field and the field variable themselves. Now, when we now move over to writing down the generating functional, and we write down the generating functional in terms of the new variables, that is the chi variables, it takes the form given in this integral d chi exponential I s. Recall that the path integral element changes does not change due to this transformation, because it is essentially a shift in the origin, and in other words the original path integration over phi carries over to path integral over chi. So, that being the case, and because the first term in the action is the integrand of the action is independent of the path integration variable chi, we can take it outside the path integral and we can write down the the first term as a prefactor to the path integral in the form shown in the green box at the bottom of your slide. Now, when there is now comes a very important point which I emphasized in the last class also, that if there is no external field acting acting on the system, then a system in the ground state will continue to be in the ground state. In other words, if I work out the transition element between ground states with j equal to 0, it must return a value of 1. Putting that into play, I have 1 is equal to z 0 with j equal to 0, that gives us that the entire expression should be equal to 0, should be equal to 1, or 1 is equal to z 0, j is equal to 0. So, therefore, the entire expression here in the green box must be equal to 1 in the special case when j is equal to 0. Now, when j is equal to 0, if you look carefully, the prefactor becomes 1 by default, because the exponent becomes 0. So, exponential of the exponential of 0 will be 1. So, this prefactor becomes 1. It therefore follows that in the condition that j is equal to 0, the path integral must return a value of 1. But the important part is that the path integral is independent of the value of j. Therefore, whatever be the value of j, the path integral must return a value of 1, and that is what we make use of, and therefore, we get the expression for the generating functional as the expression in the green box with the path integral returning a value of 1 for all values of j. And then finally, make a Fourier transform back to the original variables and write the path integral in the form that is given in the green box, which with delta x minus x dash, which is termed as the propagator being represented by the expression given in the yellow box right at the bottom of the slide. This is the Feynman propagator. Now, it can easily be shown that the Klein-Gordon propagator that we have just defined earlier in the yellow box on the previous slide, this expression which I have in the yellow box here, satisfies the Klein-Gordon equation with a delta function. Delta function as the source term. In other words, it is a green function of the Klein-Gordon equation. That is easily seen by writing out by operating on the propagator with the Klein-Gordon operator, del square x inside the integral, operating it on the e term, and I get minus I k whole square, that is equal to minus k square. So, on the operation of this del x square term on the propagator, I return a term a factor of minus k square. The m square leaves the propagator unchanged, multiplies it simply by m square, and what I have this in the limit that epsilon tends to 0, what I have is the delta function in x minus x dash, and that is clearly seen by the Fourier version or the Fourier transform of the delta function, expression for the Fourier of the delta function in Fourier space. Now, we come to the expectation values of the time ordered products. The time ordered products as per the formula that we arrived at earlier in the context of quantum mechanics is given by the expression that is given in the red box at the top of the slide, 1 upon I functional derivative of the generating functional with respect to j, and then taking the case or setting j equal to 0, where z 0 j is given by the expression in the blue box that we have already just now found out in the context of the Klein-Gordon equation. In other words, therefore, for a 2-point function, we have the expression which is given in the green box, a double derivative at different points x 1 and x 2 operating on z 0 j, and then putting j equal to 0. When we write down the value of, when we insert the value of z 0 as the expression given in the blue box, and then take functional derivatives of the expression of z 0 j in the form that is given in the blue box here, what we return is if I take the first functional derivative, I get the expression that is given in the equation just above the green box here. And please note, if I put j equal to 0 in this expression, I return a 0. That is one point that we need to keep a track of. However, for getting the 2-point function, we work out another functional derivative, the second functional derivative, and we get the one term that is independent of j plus a term which carries the value of j and then multiplied by z0 j. If I put this j equal to 0 in this, the second term which has a j embedded in it goes to 0, and z0 j at j equal to 0 now gives me 1, and what I have here is 1 upon I delta x 1 minus x 2 minus x 1. That is the relationship between the time ordered products of field operators, endpoint functions, or rather the 2-point function, in this case the 2-point function and the propagator. So, we can continue this way. We will find that for every odd point functions, 2n plus 1 point functions, we get a factor of j in the prefactor, and when I put that j equal to 0, the entire expression vanishes, and therefore, the expectation value in the ground state of a free field of the free Kleene-Gordon field gives us a value of 0 for odd point functions. For even point functions, of course, we can use the Wick's theorem to arrive at a formal value of the 2n point functions in the manner that we have done earlier for the 2-point functions, by taking appropriate number of functional derivatives of z0 j and then substituting j equal to 0, and using Wick's theorem to develop pairings of propagators and then summing over all those pairings. Now, we come to, or we derive an expression for the same propagator using Wick rotation by way of illustrating the concept of Wick rotation. The important point is that before we get into this, the important point that I would like to emphasize is that in the case of the Feynman propagator, the scheme of the poles that is envisaged, or that was used by Feynman, was that the poles to the denominator here, poles to the integrand here would appear. We will have 2 poles naturally. The 2 poles should appear in the second quadrant and in the fourth quadrant. That was, although there are other schemes, and we will be talking about them in today's lecture only, but this was the scheme that was envisaged by Feynman, the poles appearing in the second quadrant, and the fourth quadrant. Therefore, when I move from the Euclidean space to the Minkowski space, imaginary time in the Euclidean space to real time in the Minkowski space, it entails, and if I want to avoid the poles in my integration contour, I will need to integrate in the or I will need to rotate by an angle of pi by 2, the imaginary axis by an angle of pi by 2 in the clockwise direction, and that is precisely what is done, and that is manifest by the transformation x 4 goes to minus I x 0. When I substitute this x 4 equal to minus I x 0, this is the expression that I get for the propagator starting from the Euclidean propagator. Please note that the expression here in the red box is the expression that we carried forward from the Euclidean propagator. So far nothing has been done about the said about the Minkowski space, and this x 4 goes to minus I x 0. Now, we are transforming to the Minkowski space as far as the coordinates are concerned, and this is the expression we get. However, and to ensure that the scalar product remains invariant, we need to do a transformation of the wave vector also. The transformation for the wave vector will take the form k 4 goes to minus I k 0 in order to ensure that the scalar product remains unchanged, and on doing the transformation, the expression that we return for the propagator in Minkowski space is the expression that is given in the green box here. Please note, in this case there is a additional minus I here in the numerator compared to the expression that we derived using the harmonic oscillator methodology. This minus I would be absorbed when we work out the transition amplitudes, and the formula for the transition amplitudes would be modified accordingly. And the important point is, if we are using this expression for the propagator, we need to use the expression for the transition amplitudes that were derived in the context of Euclidean space, and then use this formula, whereas the expression for the propagator that was arrived at earlier directly relates to the expression for the transition amplitude in the Minkowski space. Let me go back and explain that. Yes, here it is in the green box. This is the expression for the Minkowski space. So, when you are using this expression, when using this expression for the transition amplitude or for the generating functional, the delta x minus x dash propagator would be expressed in terms of the expression given in the yellow box. So, let us move on. This is the expression for the final expression for the Minkowski space when we obtain the expression through a Wick rotation from Euclidean space. Now, we try to further simplify the expression for the propagator, and for that purpose we try to carry out the time integral or the integral in the propagator with respect to the wave vector corresponding to the time coordinate, and that is our next exercise. Again, our Lagrangian is the Klein-Gordon Lagrangian given in the red box, which can through an integration by parts be expressed in the form given in the blue box here. The propagators, as you know, the propagators when they operate on the Klein-Gordon operator, or for that matter any wave equation, they return the delta function. So, the propagators can be regarded as the inverse of the quadratic term in the Lagrangian, and that is precisely what we write here in the green box here. The Klein-Gordon operator is the box plus m square operating on the propagator, which we are writing as g x minus x comma x dash gives us the delta function. So, in other words, we can in some sense say that the propagator is the inverse of the Klein-Gordon operator in the form that it appears in the Lagrangian. Now, this clearly shows also that the g x comma x dash is the green function of the Klein-Gordon operator, as I mentioned just now. And for a Klein-Gordon field with a source j x dash source at x dash, a Klein-Gordon field with a source at x dash, the solution can be obtained in terms of this green function and can be written in the form given in the green box here. The choice of the green function will be determined by the exact boundary conditions of the problem. We can always add green functions of the homogeneous equation to arrive at more green functions, and therefore, the green functions in that sense are not unique, and the uniqueness of the green function will only follow from implementing a certain set of boundary conditions. Now, the propagators are translation invariant. We have discussed this in an earlier context when we talked about Euclidean space, and therefore, the g x comma x dash will depend only on the difference x minus x dash in some sense, because of the translation invariance of the propagators. Now, the propagator is also a Lorentz scalar. The certain properties are listed on this slide. I will read them out. The propagator g x minus x dash is a Lorentz scalar. The advanced and retarded green functions are defined in such a way, the boundary conditions of these advanced and retarded green functions are such that they vanish outside the light cone, and in that sense they obey a causality in some sense, but we will come back to this point. And in a special coordinate system, where t minus t dash is equal to x 0 minus x 0 dash equal to 0. That means two events are instantaneous in time, and as such for all points x and x dash which are space like separated, the advanced and retarded green functions vanish outside the light cone. In other words, if there are two elements, two space time events at x and x dash, and they are space like separated, then the corresponding propagators vanish outside the light cone. Let me repeat, if there are two events at x and x dash which are space like separated, then the propagator between these two space time points vanishes outside the light cone corresponding to these two events. And now we come to the solution of this particular propagator. We use the Fourier transforms. First solve the expression in Fourier space and then revert back to the position space. We use these two Fourier transform for the delta function and transform for the green function. Now, because the green function satisfies the Klein-Gordon equation, we get this in the corresponding expression in momentum space. When we work out, we get the expression which is given in the green box here. G tilde k is equal to minus 1 upon k square minus m square. Please note, we will still not introduce the I epsilon, or you may say that I epsilon is implied here for the moment, but it will make its presence in a short while. So, this is what we have for the Fourier transform of the green function. G tilde k is equal to minus 1 upon k square minus m square. Obviously, this equation has poles at plus minus m, and we now try to resolve this the issue of this pole. But before that, if we revert back to position space, we get the expression for the propagator, which incidentally coincides with the expression that we got earlier through the harmonic oscillator, and the expression is given in the green box here. So, different approaches yield the same expression. This shows the internal consistency of the framework. Now, let us evaluate the time component of this integral. In other words, we work out the integration over k 0, which we write as omega. Now, k square minus m square we write as k 0 square minus k dot k, where k is the space like wave vector and k 0 is the time like wave vector, a time component of the wave vector, and k is the space component of the wave vector, minus m square, and we club this k square and m square term and write them as omega k square. The second and the third term we club them and we write them as omega k square, and k 0 square we write as omega square. So, the expression k square minus m square is now rewritten as omega square minus omega square, omega square minus omega k square, I am sorry, where omega square is equal to k 0 square and omega k square is equal to k dot k plus m square. And we can write now the expression for the propagator in the form, when we factorize this expression and we do the partial fractions, we can write this expression in the form which is given in the round brackets here in this slide, with of course the factor of 1 upon 2 omega k here. So, this expression 1 upon 2 omega k with the expression in the round brackets gives us the expression which you have here for the k 0 component. So, and the integration over k 0 is written as integration over d omega, integration over omega, and the rest is we have simply factorized omega square minus omega k square and placed them as partial fractions. Now, clearly there are poles of this expression, there are two poles of this expression. What we will do is we will treat omega as a complex number and treat the integration as a counter integral running along the real omega axis. The singularities in the counter on the real axis, because the singularities are occurring on the real axis at omega equal to omega k plus minus, of course, they are on the real axis. They are avoided during this integration by shifting them slightly either in the upper half plane or in the lower half plane, and accordingly we get 4 types of integrals depending on how these poles are managed or how these poles are handled. We get 4 different situations. The first situation is when both the singularities are shifted to the lower half plane. The second is when both the singularities are shifted to the upper half plane. The third is when one singularity is shifted when the first singularity at minus omega k is shifted to the upper half plane, that is in the second quadrant, and the other one at omega k is shifted to the lower half plane, that is in the fourth quadrant. And the fourth is the converse of that is minus omega k is now shifted in the lower half plane, and omega k is pushed into the upper half plane, that is the converse of the one that is shown in 3. In other words, this is having singularities in the third quadrant and the first quadrant, and the third one is having singularities in the second quadrant and the fourth quadrant. And the first one has singularities in the third and fourth quadrant, and the second one has singularities in the first and second quadrants. How do we do it? How do we shift the singularities away from the real axis? Well, we introduce the usual I epsilon factor, and by using the appropriate sign for this prefixing, by prefixing the appropriate sign to this I epsilon factor, we can modulate or we can manage how the singularities are to appear or how the singularities are to be treated during the process of contour integration. Of course, epsilon will invariably be positive. It will be the prefix sign that will determine the location of the singularities. Then in each case we will convert the open counter, that is the integration along the straight line from minus infinity to infinity, will convert it to a closed counter by introducing a semicircle either in the upper half plane or in the lower half plane, as the case may decree, as the case may require, case may justify, and the criteria for which we shall just now adduce. Now, suppose and whether we close the counter by a semicircle at infinity in the upper half plane or in the lower half plane is determined by the sign of t minus t dash. T minus t dash determines whether the closing of the counter is to be done through the semicircle which is later on pushed to infinity in the upper half plane or in the lower half plane. Let us see the rationale behind it. Let us assume that t minus t dash is positive or t is greater than t dash. We write omega as r e to the power I phi, that is r cos phi plus I sin phi. So, we can write this as r cos phi plus r I sin phi. And then the exponential in the integrand e to the power minus I k x minus h dash gives us e to the power exponential minus I r t minus t dash. The t component, we are confining ourselves to the t component in the exponential. Remember, we are working in the metric plus minus minus minus. So, the t component here appears as a positive term. So, we write minus I r t minus t dash into cos phi e to the power minus I together with this I which is with sin phi gives us plus 1. So, we have r t minus t dash sin phi. So, the first E is relating to the cos phi here in the red box, and the second E is relating to the I sin phi component in the red box, and the expression we get is in the green box. Now, when t is greater than t dash, in other words t minus t dash is positive, if you look at the second factor, what happens to the second factor as r tends to infinity? We want that the integral over the semicircle, which we use for closing out the counter, contributes nothing or contributes 0 to the total integral. Now, if you look at this expression, r is positive, t minus t dash is positive. Therefore, if both the terms are positive and we want to return, we want this integral to vanish in the limit that r tends to infinity, sin phi needs to be negative. Therefore, sin phi needs to be negative implies that phi must lie either in the third or in the fourth quadrant. In other words, it is clear that in this situation the exponent term will be suppressed only if the semicircle closing the counter lies in the lower half plane. Therefore, we obtain the following simple rule: if t minus t dash is positive, the semicircle closing the counter must lie in the lower half plane and vice versa. We will continue from here after the break. Thank you.